Welcome to the Euler Project Problem 2, Part 2. In Part 1, we looked at interesting ways to use closure to compute the Fibonacci sequence. We explored memoization, recursion, iteration, and lazy lists, all in an effort to create an algorithm that was both efficient in memory and CPU cycles. And then, when we had that working to our satisfaction, and just before we lost power, we started exploring the ratios of consecutive Fibonacci numbers. And we found that those ratios converge on a constant, an interesting constant called phi. We also found out that this number phi has some interesting properties, like 1 over phi is phi minus 1, and phi squared is phi plus 1. Let's see if we can explain this. Here's the Fibonacci sequence here. And you can see it's just, A and B and A plus B. That's Fibonacci sequence. And this is Fn and Fn plus 1 and Fn plus 2. We don't know where. But now we're going to take that as the limit of n approaches infinity. All right? We'll just assume that n is getting really large now. And if n is very large, then b over a, which is these two guys, and a plus b over b, which is these two guys, should be equal to phi. So they're both going to be equal because n is approaching infinity. Right? Okay, so now we start here. We say this fraction right here, a plus b over b, is really just a over b plus b over b. But that's just a over b plus 1, and that's still equal to phi, which is also equal to b over a, but b over a is the reciprocal of a over b, so we can replace a over b with 1 over phi, because, right, they're equal, so 1 over phi plus 1 is equal to phi. Oh, we saw that, didn't we? We already saw that that was true, didn't we? And then if we just multiply through by phi, well, then we get 1 plus phi equals phi squared. Oh, we saw that one too, didn't we? Yeah, we saw that. Now, turn that into a nice quadratic equation, just like that, and I use the quadratic formula to solve it, and you get this lovely answer here. Right? Phi is equal to 1 plus root 5 over 2. Or 1 minus root 5 over 2, although since these numbers are all positive, we're probably only interested in the positive version of this answer. Okay, so now we know that the ratio of Fibonacci numbers converges, and we also know what number it converges on, phi. And we know that that number is irrational. But did you know that there is a deep mythos surrounding the number phi? The constant phi is often called the golden ratio, and it is purportedly used by artists and architects to create so-called pleasing structures. Apparently, human beings have some strange affinity for rectangles that have an aspect ratio of phi. So let's draw a golden rectangle, and I'm going to do that with this nice little turtle graphics processor that I wrote, a couple of weeks ago, just for fun. And I've defined the phi constant here. You can see it, and it's 1 plus the square root of 5 all divided by 2, right? That's what we determined that phi was. So we're going to come down here, and I'm going to draw a phi rectangle of size n. And how do I do that? Well, first of all, I put the pen down, because this is a turtle that drags a pen across a piece of paper, right? And I will choose a weight for the pen of 3. And then I will call the rectangle function with 2 arguments, which is n and n times phi. Now here's the rectangle function. And what the rectangle function does is it executes this twice. You see the do seek with range 2, right? So how do we do it? Well, we move the turtle forward by A and then turn right 90 degrees and then forward by B and right 90 degrees. And that happens twice, so it completes the rectangle. Okay, now here is the script that we're going to execute for the turtle. It's the phi rect of 200. And so let's see what this draws. There's our rectangle, little turtle drawing across the screen, and that is a golden rectangle. Now, does that look particularly pleasing to you? Do you find some artistic consonance with that particular shape? Now, I don't know anything about art. I'm not an artist. And I don't know if this golden ratio stuff is really important to art or not. Although I've certainly seen many artists and mathematicians say that it is so. What I do know, however, is that there are many interesting aspects of phi that can be expressed geometrically, and some of them may have some relation to the natural world. One of those interesting geometrical constructions is called the phi spiral. And the phi spiral, here I've got the code for that here. Don't worry about this front part, that's just positioning the pen and getting it all set up. The interesting part is this right here. We're going to loop with A starting at 1 and B starting at phi. We're going to draw a scaled rectangle. Scaled rectangle is just this up here. It just calls the rectangle function with the width and the height, which is just A and B multiplied by the scale. There's not much more to it. There's also a little bit of positioning code in there. But it first of all draws the golden rectangle. Right? It is a golden rectangle. It's 1 by phi scaled by 10. And then it says if A is greater than 40, we're going to stop. Otherwise, we are going to recur, which will draw the next rectangle, of course, and we move B into the A position, and we move B times phi into the B position, but B is phi, and phi times phi is 1 plus phi. Well, here, let me just do this and you can see how it works. Isn't that cool? Now, what many people like to do with this image is that they like to put semicircles in all the squares, as I've badly done here. And that creates this nice kind of spiral, a golden spiral. And then they like to take that spiral and superimpose it onto pictures of nautilus shells, or galaxies, or waves, or Greek architecture, and stuff like that. Color me skeptical, but I'm not convinced. Now, what I think is interesting about this picture is that it's all made of squares. And all the squares form a Fibonacci sequence. Can you see it? Can you see the Fibonacci sequence of the squares? Look at the bottom square, right? The side of that square is equal to the 2 squares on the top. And then look at the right-hand top square and notice that that's equal, the side of that is equal to the 2 squares at the top left. And you just follow that spiral all the way down to infinity. The whole thing is made up of squares all the way down, and those squares form a nice Fibonacci sequence. Now, I drew that spiral from the bottom up. I started with a golden rectangle, and then I just added squares around in a spiral. But what if I hadn't started with a golden rectangle? What if I'd started with a differently shaped rectangle, like maybe a 3 by 5 rectangle? So we start with a nice 3 by 5 rectangle here, and we can make one cut to make a 3 by 3 square right here. So we're going to make that cut. Now we got a 3 by 3 square here, but that leaves us with a rectangle over here. Well, we can cut this square into that rectangle into a nice 2 by 2 square. So this is a nice 2 by 2 square, but that leaves us with another rectangle. Well, we can cut that rectangle into two 1 by 1 squares. And we're done. So let's see this happen on the screen. I'm going to call the square spiral method for a rectangle that is 3 by 5. Now, a square spiral is defined over here, and we're going to find out which is the length and the height, because we need to know the min and max. And then we're also going to do a little math to fit everything on the screen. The screen is 1,000 by 1,000, the way I've done it, so I'm multiplying by 980 here, or actually dividing by 980. And the reason for that is that I want 10 pixels on each side, just so that it fits in the screen with a little bit of a border. I multiply by that factor, of course, and then I print the length and the height. Then I do a little bit of repositioning of the cursor, and in the end, I draw the initial rectangle. And then I call square the rectangle. This is the function that actually does the spiraling. Square the rectangle's up here, and it's I'm not going to say it's straightforward, but here's the length and the height of the rectangle. And if we've gotten a 0 height, that means that there's no more squares to draw. We're out. And by the way, that means this is a rational number. We've done all the divisions we can, and we've gotten down to 0, right? So that's cool. If we decide that the length is less than 1, well, then I'm going to say it's irrational. This is not perfect because there are no irrational numbers in a computer, but it's a good initial first guess, right? It's probably irrational. Okay, after that, then we're going to do the division. We do the division to find out how many squares we can draw. That's going to be n, and we get the remainder. That's the rectangle that's left over, or the width of the rectangle that's left over. Then we draw the squares. This is where we draw the squares here. Zoop, 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 zoop. And then we call square the rectangle for the remainder. So it's just going to go round and round and round and round and spiral. Okay, so now let's see it. Let's run it. And here it goes. It draws the original 3 by 5 rectangle. Okay, there's the first one, there's the second one, and then the final two, right? There we go. That's the whole thing. Okay, so now let's do a little math. Right? Now here's 5 over 3. This is our 3 by 5 rectangle. And 5/3 is really just 3/3 plus 2/3. And that's really just 1 plus 2/3. And that's really just 1 plus 1 over 3/2. You get that, right? Well, that's just 1 plus 1 over 1 plus 1/2, which is just 1 plus 1 over 1 plus 1 over 2. Oh, looky. 1, 1, 2. Okay, well, let's do a more interesting one. Let's do the square spiral for 19 by 23. All right, and it draws the original rectangle. There's the first square. Ooh, skinny. And then we're going to have 1, 2, 3, 4. Woohoo! And then 1, and then, ooh, look at that, 3. So 1, 4, 1, 3. 1, 4, 1, 3. Cool. All right, so let's check that this repeated fraction works out right. So 1, 4, 1, 3. That's the boxes that we got for the 19 by 23 rectangle. So let's see. 1 plus 1/3. This right here, that's 4/3, right? And then you put that, under 1, and you get 3/4 plus 4. Well, that's going to be 16, 17, 18, 19/4, right? But now you put that under 1, so you get 4/19 plus 1, and that's going to be 19 plus 4 equals 23 over 19. Ha 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 ha. All right, well, let's try an irrational ratio here. We'll do the square root of 2. Run it. right, here comes the rectangle. Yeah, square root of 2. Okay, draw it. Yep, good. Oh, 1 and 2. Ooh, 1, 2. Oh, 1, 2. Oh, 1, 2. Oh, 1, 2. Look at that down there, huh? It's 1 and then a bunch of 2s. And it's irrational. Okay, let's see if this works out. Here's the square root of 2, right? And the square root of 2 is equal to 1 plus the square root of 2 minus 1. Yeah, so that's kind of obvious, right? And now the next step here, well, that one might not be quite so obvious to you, but you can work it out with basic algebra. 1 plus 1 over the square, 1 plus the square root of 2. So all of these things are equal. But notice, there's the square root of 2 there, and there's the square root of 2 there. So by replacement, we can take this square root of 2 here and just replace this expression, which is 1 plus 1 over 1 plus the square root of 2. But we don't need, well, wait, first of all, we've got all these 1s here, so let's get rid of those. We'll just call that a 2. That's 2 plus 1 over 1 plus the square root of 2, but that square root of 2 can be replaced with this expression, which is 1 plus 1 over 1 plus the square root of 2, and then we can take this 1 plus 1 and turn it into a 2, and, well, you can see this is going to go on forever, isn't it? I mean, this is just going to be 2 plus 1 over 2 plus 1 over 2 plus 1 over 2 all the way down. So, yeah, it kind of works, doesn't it? It's magic. But this was all supposed to be about phi. What does all this have to do with phi? Well, we already kind of know that, don't we? But you know what? Let's just give it a shot. There it is. We're going to do the square spiral of phi. Some of you already know. Some of you have guessed. Here we go. Okay, here comes the rectangle. Okay, the first square. Good. Okay, the next square. Oh, one square, another. Oh, one square, one square, one square, one, 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 one. And it's irrational. Look at that. Nothing but ones. Now, of course, we've seen that geometry before. It was the original phi spiral. But now we've learned something interesting about the number. This is the continued fraction for phi. And if you look at it, you'll realize that this means that phi is the most regular and symmetrical of all the square spirals. It's the perfect square spiral. But does that matter? I mean, so what? Well, it matters if you're a leafy plant, because the phi square spiral, the regularity of that spiral, is your best bet at making sure that you get plenty of sunlight to all your leaves. Imagine that you're a plant. Imagine that as a plant you sprout leaves. Imagine those leaves sprout out from the center of your stem. There are lots of plants that work this way. Now, let's say that you sprout one leaf every day, a new leaf every day. How are you going to arrange these leaves so they don't cover each other up and block each other from the sun? The trick, of course, is to rotate a bit before sprouting the next leaf. Right, so we sprout a leaf and then we rotate, sprout another leaf, rotate, sprout another one, rotate, rotate, rotate. Now, the question is, what's this angle? How much should we rotate by? So let's do flower spiral. And we'll choose 180 degrees for our rotation angle. And the flower spiral function is pretty simple. We're going to do a 250 petals, or 250 leaves, if you wish. And we're going to make it go fast. And we're going to, for each petal, we're going to turn right by the rotation amount. Then we're going to move forward by the radius increment. We're going to draw a dot, and then we're going to move back to where we were, and then we're going to go around that again and again and again and again. So what you will see is us drawing around using the rotation and outwards using the radius increment. And if we do 180 degrees, well, I think you can predict what's going to happen with 180 degrees, can't you? I mean, for goodness sake, it's just going to be going left and right out in linear lines, isn't it? There it is. Round and round and round, 180 degrees for each leaf. This would probably not be a good strategy for a plant to use, although it is the strategy that ferns use. It's just that ferns also move linearly at the same time they're doing that rotation, so that works out for them. The leaves do get enough sunlight. But if you were just rotating around a central stalk, this would not be good because your leaves would be covering each other up. Now, if we chose angles like 120 degrees or 60 degrees or 90 degrees, you know what would happen, right? We'd just get these nice lines of leaves covering each other up. So let's try 120 degrees. And what we're going to see, of course, is 3 lines radiating out from the center. Exactly what you'd expect here, 120 degrees apart. So we'll let that one finish. And, we could try 60 degrees, but that would just be 6 lines radiating out from the center, right? So there's 60. Let's see what it does. It's going to be, 6 lines. And, there's a lot of space out there for your leaves to get sun, and they're not getting the sun in all that wasted space. So what if we use some strange fraction like 11/13 or 19/23? Well, we could try that, of course. Here's 19/23, but the result of that, of course, is just going to be 23 lines, right? I mean, we can't actually use a rational number, can we? Because if it's a rational number, we're going to get 23 lines. Look at that. That's an interesting spiral, isn't it? Wow, that's so cool. It's a spiral, but wait. No, it's not. It's 23 lines, isn't it? It's 23 lines. It just kind of looks like a spiral. Let's count them. Come on, we've got to count them. Okay, there we go. There's 1 at the top. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Yeah, no, I don't think we can use a rational number, guys. Okay, so if we can't use a rational number, let's try an irrational number, like, maybe the square root of 2. So this is what you get when you rotate by the square root of 2. And it's not bad, is it? It's a nice, even distribution of leaves around the center. You see those clockwise spirals out at the edge? Count them up. You'll count 17 of them. That's interesting, isn't it? But look in the center now, and you'll see that there's counterclockwise spirals. There's only 7 of them. Is that the right ratio? 7 to 17? I wonder. You know what? Maybe we should try phi. Don't you think we should try phi? I think we should try phi. Okay, so let's try the phi spiral, shall we? The first thing to notice is that you don't really see a spiral show up real fast, do you? You're starting to see one now. It's kind of a counterclockwise spiral. Oh, wait, there's also a clockwise spiral. Oh, look at that. You see both spirals. They both sort of appeared almost at the same time. And they seem to be about evenly spaced, don't they? All right, let's do a little bit of counting here. How many of these counterclockwise spirals are there? It's going to be difficult to count them, but we'll start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21. There's 21
of the counterclockwise spirals. How many of the clockwise spirals are there? It's a little difficult to count them, but we'd have to start in here. Maybe we can see them a little better here. So I'm going to start with this one right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 and 21. Huh.
Does it surprise you that 13 and 21 are consecutive Fibonacci numbers? Anyway, you can prove that the angle of phi is the best possible way to distribute the leaves around a radially growing plant. And this is why golden spirals like this are often found in plants that grow radially. But does this mean that the plants know how to calculate phi somewhere in their genes? No, not at all. What you are looking at here are drops falling into a fluid that's moving outward, and the drops repel each other electrostatically or magnetically or something. And it just so happens that the balance of forces of all these repelling dots in an outwardly moving fluid choose the angle of phi to balance all the forces. That's where the equilibrium of the forces is established. This is not something that plants know. This is just basic physics. So you see, the golden ratio is rooted in physics. The physics of balanced forces. The physical angle that balances the forces of repelling objects trapped in a radial expanding medium. And it shouldn't be too surprising that phi is the appropriate angle that balances those forces, because phi is the constant that provides us the most symmetrical and regular of the square spirals. Wait, did that actually make any sense? I don't know. I'm just a software guy. Anyway, how about that nice little turtle graphics program I was showing you? You like that? Well, in part 3, I'm going to walk you through the code because it's actually kind of interesting. So you're not going to want to miss the next exciting episode of the Euler Project. Euler Project Problem 2, Part 3, Turtles and Channels.